Okay, good morning, everybody. This is our OCP HPC subproject regular call on the 27th of May 2025. So let me share my screen. One wrong. Hopefully you can see the notes. Yep. All right. So I don't believe there's any new attendees here today. I think everybody's been before. So no introductions needed. So the first thing I wanted to bring up was our New Frontiers proposal. The good news is we still haven't been rejected, if there is good news. And the bad news is it's still in process. So let me just, if I bring this little note over. So Jason Holder, not sure if you can read this. I can't really zoom in for some reason. So he basically said, I wanted to provide you with an update regarding the RFP for the New Frontiers project. As you are aware, this project has been on hold for some time while we await further information. We are getting closer to receiving the necessary feedback that may allow us to restart the work on the project. However, I must emphasize that no decision regarding the program's viability has been made at this time. In the meantime, we would like to request confirmation from all responding firms that their proposals remain valid and will continue to be valid for the next 120 days. Please send your confirmation by May the 30th, which is, I believe, this Friday. Should you have any questions or require further clarification, please feel free to reach out to him directly. And he said he'll keep us updated with any more information that becomes available. So that's the reason for this topic. Essentially, and if I bring up, I did open up the proposal. Where did I put it? So here is our proposal. And essentially, these are the participants. So we've got Carno, we're providing the chassis for mounting our modules to. And Lumineer, we're going to be doing the design of the module itself. Lattice, we're helping out on the system management side of things. Amphenol and Lotz on the universal topology interconnect and various other aspects. On the interconnect side, Light Intelligence, we're providing an optical solution, active optical cable solution, and Avicenna, we're in there as well on the active optical and a not co-package, but onboard optics. And Jabil, we're supporting Carno in any manufacturing that would be needed in the USA. So that's a list of companies that I need to basically talk to everybody and get their confirmation that they're happy to carry on forward with our bid in the price that we've put in place. So if I just bring up while I'm here, if I just bring up the costing spreadsheet. Okay, another right chart. Hang on, let me see if I can make this one bigger. There we go. Okay, so it's by company. Just got to remember the way we structured this. So each page is showing each company's cost proposal. So I guess in terms of the companies that are on here, we've got Lotz and Carnot. So I guess, Chloe, I'm not sure if you can speak to this off the cuff. I guess you did see the agenda item. This was your proposal at the time. Are you prepared to honor this, assuming the project could go? I mean, the project, we were supposed to be notified of the project at the end of February. It's now the end of May, and they're saying it could be another 120 days before anything gets awarded, if it does get awarded. So that would take us up to end of June, July, or so that would be the end of August compared to the end of so basically like a 6-month delay on the project. So are you prepared for this proposal, this cost proposal, to stay as is? And so I can give an affirmative reply to Jason or not?
I believe that it is still doable on our side. The thing I'd like to confirm with my team, so I was wondering, could it be possible to rehave the link of the proposal?
Sure. Actually, I can certainly do that.
Perfect. And then in how many days can we give you an answer later this week, for example?
Yeah, I've got to get a reply to Jason on the 30th, so that's on Friday, I believe.
Okay. I assume that it's 99% yes, but since I'm the only one from the team, I'm just gonna double confirm with the proposal in hands with the team and get back to you tomorrow.
All right, that sounds great. Thanks, Chloe. That's
Yeah.
what we needed to hear. So yeah, what I'll do is I'll probably post. Hang on a minute, there's a lot of noise coming from outside. Just a minute. Um, I'll post all of this on the wiki again. I'll repost it with the minutes, and then I'll send you the link. So then I'll send it out for everybody that's not on the call, so they can all see their various bids.
Yeah, thank you very much. I'm talking to my team at the moment, so perhaps maybe I can send them the link and by the end of the meeting, I'll let you know.
Okay. All right.
Thank you
Thanks.
so much.
Okay, that's Carnot. Luminaire not on, Lattice aren't on. I don't believe. If anybody's jumped on since, let me know. Oh, hi guys. I see we got a few more people who've just joined us. E-Guide Marissa from Molex. Hi.
Hi, Alan.
This is your first time on this call, right?
Yes.
Okay. If you don't mind, could you do a quick introduction of yourself, please?
Oh, yeah, sure. I'm Egid Marissa with Molex. I represent Molex really mostly in PCI SIG and SFF and fiber channel. And I know Molex, we need to get more involved in OCP, so I'll be the Molex rep in these meetings.
Okay, welcome aboard. Everyone's welcome. So
Thank you.
thank you. And good morning, Olivia. I see you've just joined us.
Morning, Alan.
And good morning, Raoul. I see you've joined us. Just update my. No, I have you here, Raoul. There you are. And Lisa, hi.
Lynn. I saw the second item on the agenda and I jumped on the call.
Right.
The megawatt rack.
Okay, that's everybody. Right. Yeah. All right. So yeah, so we're just going through the New Frontiers proposal in terms of reaffirming our bid. So Amphenol gave us a cost. So Z is not on the call, is he, or nobody from Amphenol? And then Lote. So Howard, I don't know if you can be representative of your group or one of your guys there. So does this proposal still hold for you guys, given the delay of approximately 6 months from a kickoff if we do get funded?
I believe we're probably okay with this. For the portion that we have, I don't believe there's a lot of changes.
Okay, it's great to hear. All righty. Okay, then I don't believe there's anybody on. No one from Light Intelligence. No one from Avicenna. All right. Okay, and I'm happy with mine, just to state it for the record. So that works. I believe if we can't get a consensus from everybody contributing, then I think that will invalidate our proposal. I don't think we have an opportunity to resubmit the bid. I could ask Jason that question, but probably I'd rather not until I get confirmation. If everybody else concurs with the rest of us, with us three, then that should be our best position to go forward with this. Okay. All right. So, like I said, it's not bad news for us, I don't believe. Maybe the way we structure the solution might change slightly as well. I don't know if we should start to think about that, but you know, whether anything changes. But I guess if that does happen, can we do that within the costs we've got? It would be the other question. But anyway, so I think just affirming that our proposal is still good is the best step forward right now, and keep us in the game. Any other questions on that? No. I'll just make some quick notes here. Yes. Okay. All right. Right. So that's basically that topic. So the next one I want to take a bit of a reset. Well, not a reset per se, just a couple of months ago now, or a month or two ago now, we did discuss all the updates from NVIDIA, if you remember rightly, and including I flashed through this presentation here that I just pulled together, the highlights, and I guess some of the interesting things that we are seeing from NVIDIA is their Vera Rubin platform is going entirely liquid cooled, as we can see here, into a blade format with a sort of a mid plane rather than maybe a back plane. Some interesting questions were left in terms of on the other side of this mid plane, I think was where the NVLink switches were in the connections. Whereas these modules are, if you look at the way they're orientated, they've got four modules here, and they're elongated. And I believe that what we're looking at here. I think these are the Vera chips and these are the Rubin chips. But I believe that this will include the new package, which is going to have 4 of the GPU dies, and so 16 HBMs. So they're, if you, in fact, we should have seen it. I'm not sure if I captured a picture of that here. That's the switch card on the other side. That's the 3 NVLink switches. That's the Blackwell platform. Now here we go. So that's the first Rubin, which is the same setup as Blackwell, 2 die, but they've added these new I/O die on the end. So your IOs are now separate dies, which is interesting in its own right. And this is the new Rubin Ultra. So there's 8 die in here. 8 of the processing dies plus IO dies at either end. And I'm not entirely sure, assuming these dies are identical. You see there, it looks like these are rotated by 180 degrees, but they look identical otherwise. So it looks like this die in the middle here is yet another IO die, but is a bridge die. I don't know if anybody knows any real details on this, but so you've got an IO die. Go on, anyone? Nobody has. So anyway, so I'm not exactly sure of the structure of this, but you can see that the package is getting more and more elongated here. And so I believe that
I'd be surprised if actually they keep that as a single package. But
in a single package, this thing.
yeah, I'd be surprised. Maybe a module, you know, like Grace Hopper, right? Where they would have Rubin, right? Because if it's just twice what was there before.
Well, I believe that's the idea because Jensen started so with the Grace.
Yeah,
with the
each die now is a GPU, right? In his definition.
Yeah, each die is now a GPU in the definition. So he started to break that out because the package was obviously in his marketing term. I mean, on the one front, you think he's just using it to give exaggerated scale, but in reality, as they put more and more die inside the package, it makes sense to be talking by the GPU die.
Right.
I mean, it certainly looks like it's a package. And from what I've seen a number of years ago when I saw TSMC's roadmap, I did see this sort of approach in they showed pictures like this in their roadmap. So that's my understanding. And talking to a few people that are trying to build chips with this same sort of architecture, they seem to be all in the same boat of saying these packages are going to get elongated. But yeah, and the only other thing we've obviously seen with Blackwell, although it's not really shown here, is they've gone towards this puck type architecture where it's just slightly bigger than the package with all the main power supplies, and it's like some zero insertion force type socket, I guess, that plugs onto the bigger board to give some level of configurability and serviceability for the ODMs. That's the only thing there. So and based, again, I do need to do a bit of a deeper dive into this, but based on the numbers that they're talking about, the number of dies, if this is the elongated package under here, then you've got 16 GPUs in this blade, which I think I remember seeing in the keynote. So and this doesn't look, although it's elongated, it doesn't look that big. So it looks like they've gone to this entire puck size. So it's certainly interesting.
If you look at the numbers that they quoted for Kyber, right, the rack with the perpendicular connection and what you're showing there, right, on the left, it's per tray. It's not gonna be 16 tiles.
It's not.
It's not. It's not right because they have 12. Right. I think they have what 12 vertical blades across 3 trays. That's 36 times 8, and you get the whatever the 576.
You've got 18 blades here.
Right.
18 blades times 16 would be 18 times 16 is 288, and then you would multiply that by then they've got three blades in a chassis, is it?
I thought don't they have like four? They have 4 trays.
So 4 times 4 then.
Okay. Right.
That'd be 1,152. Yeah, they
I mean, right? 576 divided by 18 divided by 4 is 8, right? Which is 8 tiles, which is effectively 2 Rubin Ultras, right?
okay.
So again, right? From a density perspective per blade, they're not changing things. The thing that they do is, right? 18 vertically in a chassis means that they're like ultra low profile, right? And they're using those new, I think for the host, there's those new dims, right? The SO dims or whatever.
Yeah, they're using for the Grace part, or for the Vera replacing Grace.
Part, yeah.
But if you look again, if we look at that blade, you can see there's the 2 Veras there and there.
You lost the sharing, I think.
Oh, did I?
At
Interesting.
least I don't see it anymore.
Can anyone else see it?
Oh no, actually I see it now. Okay, I don't know. It stopped and came back. Sorry.
Yeah,
Yeah,
so
you got
these,
the 2 Veras.
these are the 2 Graces, Veras.
Right.
And then you've got the 4 Rubens, but
Right. So it's going to be replaced by 2 Rubin Ultras.
okay. All right, so maybe they'll rotate them and then okay, all right, now I'll buy that.
Yeah.
So this is probably the Rubin version 1 with just the same 2 dies as Blackwell.
Right, exactly.
And then it rotates, and you've got the 8 probably going up and down here, or however way they're going to do it. Times 2. Okay. So, and also they've got, like our ideas in our approach, we were saying we need to conductively cool the SSDs or the memory, any CXL.memory, etc. So Solidigm is now introduced drives which can do exactly that. So that's what was introduced here. And they're also cooling the QSFPs. I believe they have some IO on here as well as SSDs. And so so there is no air cooling in this. So unlike Blackwell, well, actually, the interesting thing is the GB300 has now gone to 100% cooled as well, as you can see here. So now they've got the water pipes everywhere going to the GPU cards. It's basically cooling everything. Everything's liquid cooled, and they've got this. This has replaced the bank of fans. So if you remember I'm not sure if I have an old picture in here of the old, I don't, of the old Blackwell. I'd have to bring up the old, one of my previous presentations. But anyway, going back to that, this was a bank of fans because it was hybridly cooled. You air cooled these cards here, and then it was liquid cooled for the Grace and the Blackwells. But now they've gone to 100% liquid cooled on the Grace Blackwell 300. That's a big upgrade there. So this 100% liquid cooled, which is where we've been with our original architecture, well, not, the one we've been talking about, the HPCM, and the one that's in our proposal, saying we need to go to 100% liquid cooled and conductively cool pluggable items like SSDs. That's exactly where NVIDIA have gone. So we had the right idea 4.5 years ago, guys. It's just we had no money to do anything about it. And NVIDIA have now done it. So we were 4.5 years ahead of our time. If only AMD and Intel listened, we could have skated to where the puck was going, but sadly not. So when you look at this as well, obviously we have our wall of compute. Maybe what I should do is I should bring up ours just for everybody's reference here. Let me just see if I can find our presentations. Hope this is the right presentation, but so we obviously had one thing we had was consistency around a module. So this is one of my big slide decks, I think. Yeah, so let's see if this has got our so here we are. If you remember, what we were going for was, I guess, one of the things that that I've been sort of personally saying is that everything's going to roll up inside these modules, and you'll have one common building module block. Why do we need NIC cards, etc.? It's going to be media basically, and media could have on media acceleration, near memory acceleration, and then the I/O will come out of the processing chips. And if you remember rightly as well, I was saying that the processing chips need to have one interface, one I/O interface on them. And that is a memory interface, because the native language of all processing it talks to memory. When something pops out of a USB port or an Ethernet port, the software engineer talks to a chunk of memory, and miraculously it squirts down a pipe. And so, I said, everybody's compute needs to have the same chiplet memory interface. And then you can put I/O chiplets to your favorite standard. So, again, all these ideas we've been presenting are actually being implemented by NVIDIA. So going back to this again, we're seeing they've added these I/O dies. So you can imagine these die interfaces here are one consistent interface, one would assume, right? Ideally. And even to the HBM, I've argued that the processor chip just has one I/O interface where you can connect HBM, any type of memories basically, and you have an I/O bridge. If you want to go to transport I/O, electrical or optical, or in any different electrical standard, you do that with these I/O chiplets. So we're seeing this disaggregation happening inside the package and reassembly inside the package. So network cards are going to disappear. These I/O chips are effectively tomorrow's NICs. So we don't need NICs anymore, or DPUs. Any DPU functionality will go on in these I/O dies. So what we've been predicting in this work group is absolutely right in my view. We're still going to come down to these individual modules. These are some old diagrams. This is a very old presentation. Where you've got this compute die with I/O capabilities, and you can either couple I/O, tremendous amounts of data. It's as low in energy as you possibly can, as lower latency as you possibly can into this beast, as well as its local HBM. Obviously that's the lowest energy, the highest bandwidth. But we want CXL. I was just chatting to Mitch at the beginning of the call. We want multi-terabytes per second between these media using ideally this CXL interface, especially if we can get the CXL interface latency down. It's another argument. Then we can get many terabytes per second at low energy to the compute. So this tight coupling is what we've always been talking about, and this being completely liquid cooled is what we've always been talking about. So, I mean, you know, in my view, we've been on the button, and NVIDIA are the only one this actually making the progress, but we were ahead of the game. Arguably, you could. This is where I guess I've been sort of saying when I presented this a few weeks ago or last couple of months ago, I said I need to digest this and think about the implementation that we're seeing, because obviously this is real, it's not a bad implementation. It's stuck with the 19-inch or the 21-inch rack, the rack approach. So you're getting depth density as well as you're getting sort of three-dimensional density here, which you could argue is better than our approach because we've got these modules, and to a certain extent, we're putting them onto a wall like this, and so we have less depth density. But the key thing we have differently here is our 3Dization is all about the media being, as much media being coupled as tightly as possible to the processor chip. And the other idea that we had here is these media can also turn into I/O, as we were just discussing. You know, either you attach memory or you attach I/O because you want to talk to a neighbor. So at system design time, you can decide whether you want memory or I/O to you know, if you need more compute, you may not want more connections to neighboring compute. If you want more memory on a single compute module might make sense. Whereas today, you want more memory, you need to have to buy more NVIDIA B200s or whatever to expand your memory capacity, even if you don't need the extra compute. So this would give you that flexibility. This modular approach also gives you, by being very Lego brick, gives us the ability to be fully heterogeneous. If the processor guys got on board with this as well, then I can put a CPU here and 10 GPUs or 10 CPUs and 2 GPUs or a bunch of FPGAs or a bunch of other custom processing chips, depending on what job I'm trying to do. So this gives us full flexibility, right? So, and the other thing about this was this media can turn into I/O, but as we all know, and we've discussed on this call on many occasions, and one of the biggest criticisms about this approach is it becomes a cabling nightmare because you're going to be cabling between all these modules and it's an absolute mess, and copper cables are just getting fatter and fatter as the speeds go up. And shorter distances. But we said, well, okay, if we're designing for active cables and on package on board optics, so optics is very thin fibers, and so that could dramatically improve the connectivity here at this sort of scale. So looking to where the puck is going, I was less concerned about this, and I also believe that at some point, a bit like robots, you know, gantry robots service tape drives like IBM tape drive systems. I saw that gantry robots could service media here, and or service the wiring of these networks. And again, if these networks were built for one domain-specific computer, you can wire this up for a domain-specific computer or wire up for another. It can stay static for reliability reasons, or maybe it can be reconfigured on a maybe a monthly basis as different types of compute are needed with it. So this serviceability idea came through. So I'm still, if you look at this, you can make your corridors more narrow, which we were showing here. We were showing the density of the footprint. You can bring these corridors closer together. If a human needs to go down here, then obviously that is probably the limit of the corridor, but you haven't got to eject big long drawers like you do out of these 19-inch racks. So you don't need as much space. And arguably, you know, if you only need an emergency for a human to go down here, if this is all maintained by robots, by gantry arms and the rest of it, maybe there's less need for that human entry point. But obviously, if the robot breaks down, then you're going to be screwed. So there are limits to the density we can get here. And the other thing is we can then design the power delivery and the cooling into the wall. And so when we're talking about 1 megawatt racks now, guys. So we're talking about 800 volts DC, either in 0 to 800 or plus and minus 400. That's what's going on. If you've been following the Open Systems for AI sub-project or strategic initiative presentations over the last couple of weeks, been some wonderful presentations from the infrastructure and power people. A great place to learn, and I'd recommend you all go and watch them. They are really informative. But when we architected this, we were thinking about power and delivery, and it was how, if you remember, I've done this in my regional summit. It was between these power pins and the actual load of the chip. We could be. And from the 800 volts now, we could be a matter of a couple of inches between. So the voltage, the power losses between the infrastructure power and the load, the point of load, is a lot shorter. And so there's a lot of reasons for this infrastructure. And then you think of the liquid system that you're doing here. And so I've been talking to the immersion folk. I've been trying to analyze the cold plate approach. And you can see, again, if we just go back to here, you can see that this is a pipework nightmare. This is a water manifold in the middle here with connections all over the place, right? It's a bloody mess. And it doesn't look cheap, and it's very specific again, whereas we're trying to get generic. And then the more I talk to these liquid cold plate people, you're dealing with these pressure drops. There's a, you know, it's like a load, you know, an electrical load. You know, you've got to deal with all of these pressure drops and the flow of the water and the conduction and the cooling. This is pretty damn complex. And in talking to some of the immersion folk, you know, the immersion looks tremendously easy in a lot of ways, that you just dip the whole lot in a bunch of fluid. And again, we have in our idea, this chamber on this side was a mini immersion tank, right? But the thing is we did bring the water in like this, and so we are dealing with pressure drops to each of these modules. And so I've been sort of rethinking about how could we connect these into an immersion chamber, but there's a lot to learn about the immersion, the oils that are used, the single phase versus dual phase, the amount you can cool or can't cool with immersion. And then, and Olivier, you might be able to help out here. We're seeing backside power coming into play, right? So when you think of backside power, you're going to bring the power in from the top here, and then the other side is just going to be I/O, but we still need to cool this beast. But if you think of backside power, you think we attach copper onto these things to sort of extract the heat with a thermal paste. So maybe the copper conducting for the thermal, taking the thermal heat away and to the liquid, could also be the copper power delivery of the voltage to the back of the die. So you actually do the cooling and the power at the same time. Obviously, your liquid needs to be non-conductive between the two. because or maybe, and Olivia, I'm not sure if you can help out here, but I was thinking on backside power, why bring the power and the ground to the back of the die? Why not just bring ground to the back of the die? That we have many, many ground pins and still bring power from the front of the die was one of my thoughts. And I didn't know whether the industry is considering that as an option or both power and ground to the back of the die. Is Olivier
Well,
still on?
we've yeah, I'm still. We've actually had to put. Well, we've been considering putting, backside VRs mostly to actually bring power, not ground, to reduce the losses through the routes from the VRs all the way to the package pins, right? So, so we would still want by default to bring power mainly from the bottom, or
So-
from the opposite side, I should say.
So you're thinking power from the top and ground remains on the bottom.
Possibly, yeah.
Interesting.
So Alan, power is differential. The days of there's ground and there's a plus power pin is long gone. Fully experienced at Ceabris.
Right. So when you say differential in the sense of low impedance,
No, if you have a plus pin, you have a minus pin. Tightly coupled,
You
just
always
like
pair them, he's saying.
right? So in that sense, you would have the ground on both sides, right? On the back side as well as the power, you're saying, Mitch.
correct. Whenever you say power, I think two wires.
Yeah. No. Agreed. But I guess that's a good point actually. Yeah, that's an interesting point. But if you had a power on one side of the die and a ground on the other side of the die, and we're talking 0.1 of a millimeter, those power and grounds are actually very close to each other as long as you've got an AC coupling capacitor through that die as well at the high frequency side of things.
Okay, I won't argue with the chip architects and so on and whatever. They might do something like that, I suppose.
Yeah. But to your point, and I guess that's it. When you start to think about power coming to this side of the chip, you start to think about, well, hang on a minute, where the bloody hell am I going to put my heatsink? Or do I need a heatsink that has the heatsink typically has copper involved, and either a vapor chamber if it's air cooled, or flowing water or liquid through it, non-conductive. If it's non-conductive liquid and you've got some isolation between the powers and grounds, it's how do you, if you deliver all your power to the top side and you deliver all your IO to the bottom side, where do you take out your heat? is a question that's being begged. So unless you design the backside power with how you're going to cool this beast, now the trouble is we have no control over that. The Intels and the TSMCs are going to decide how that's done, I guess.
I'm sorry to interrupt. I have to leave, but as a representative of Carnot today, the sooner we receive the proposal, the sooner we're going to be able to confirm.
Yeah, I'll send that. I'll put it live after this call, Chloe. I just got to drop the car off for a service, so I'll get it done.
Perfect. Thank you so much.
Tomorrow morning by the time you get there.
Perfect. Okay, perfect. So I'm sending you, and if we can also rehab this presentation on the wall of computer, I think we can have also some reflection on our side. So I'm just putting in the chat my email address with the 2 documents that we required.
Yeah.
And the sooner we have it, it's a holidays, Thursday and Friday in France.
Oh, right.
We only have tomorrow with the
Okay, you should have it first thing tomorrow morning, Chloe.
Yeah. So consider that tomorrow morning will be the end of the day for us.
Well, so first thing your morning, I'll have it out today here, so it'll be first thing in the morning your time.
Perfect. That's appreciated. Thank you so much.
No problem. Thanks, Chloe.
Have a great day. Bye.
And by the way, Chloe, the proposal itself describes all this wall of compute concept anyway, so it's all in the proposal.
Oh, okay, perfect. Good. It was just great. The visuals were quite explicit, so
Yeah.
perfect. If it's all in
Okay.
there, then it's perfect.
Yeah, thanks, Lloyd.
Thank you very much. Have a great day.
Bye. Yeah. So I guess Olivia, I mean, is there consideration as to well how the hell you're going to cool this when you bring backside power in? Is that solved?
Well, I can't really say it's solved. We have prototypes that where we played with that, where again, right, the backside VRs have their own effectively, cooling plate, as you mentioned, and then the opposite side has just more traditional cooling. But yeah, it's basically we do a sandwich of cooling sandwich, right? So
A
that's the
cooling
way
sandwich,
to
right?
address
Right.
it. Yeah.
So
Again, right? Yeah.
So
I think
I guess Olivier, I mean this is a fairly direct question. Obviously, here in OCP, we're looking at this from a system perspective, right? And we're trying to get, I mean, this work group, I mean, people can tell me their view. I think we've been very innovative in seeing where the industry is going to go, and we were 4 years ahead of our time, yet we were completely ignored, and now NVIDIA is delivering on a lot of our ideas, albeit with their own tweaks and doing but they've got real engineers working on this with real money, whereas we're all volunteers. Is there any possibility that Intel can say, and or TSMC, obviously they're not on this call, can say, hey, we're bringing a new solution to the market with this backside power, and the industry's got to work out how to solve the delivery of the power and the thermal management, which is clearly a system level issue. Let's open up what we're doing so that the industry can try and help. Or is it going to be done under closed doors and we'll have to wait and see what Intel tell us and TSMC tell us?
Yeah, well, I'll get back to you on that. I'm not the one who decides that, right? So I'm always open to share things. So
yeah, I guess that's the problem. I mean, this is a challenge that we have. I mean, we can. I mean, I can second guess, and I think the solution really is we're extracting the heat from these things with chunks of copper going to liquid, and these power rails are so high current that we keep talking about it's how hot they get. So cooling the power delivery is also a requirement. So you kill two birds with one stone there. But if you design the liquid attach, or such that you can do both the power delivery and the cooling. And so I've got some ideas on that, but again, those ideas can be flattened depending on how the chip guys do this backside power. And so understanding how they're doing it can either help us say, yes, this will work, or say, hey, could you change this in your backside power or not, etc.
Yeah. I'll get back to you if there's more that we can share.
Yeah. I think it's one of those domains. It's where and I fear. I mean, my biggest issue and complaint is that it's not just Intel, it's AMD as well, and in particular, it's we seem to follow what NVIDIA do, like OAM followed SXM, but we're 5 years behind. We got to be working out where it's going, and we want to get ahead of it, so at least we arrive at the destination at worst case the same time as NVIDIA. That's my view anyway. And if we can do that as a community, then all the better.
I mean, I don't disagree with you. I would say that from a rack perspective, right, from the Kyber rack perspective that NVIDIA is showing, Cray has been doing that with their high-end HPC racks for 10 years now, right? So it's not
right.
NVIDIA is bringing that to the world because it was kind of like confidentially done, but the racks that we use on again Aurora Frontier, El Capitan are old, perpendicular, fully liquid cooled cabinets that are effectively have the type of densities that Kyber is presenting to the world as a great innovation, right? It's not.
Right. No, fair enough. I mean, you are well. I guess New Frontiers. I've not seen yet El Capitan. Is there any public information on El Capitan?
Yeah, they're all the same rack. They actually, it's funny because historically they were the racks that Intel was co-developing with Cray back in 2015 or whatever, right? When Cray was not part of HP, right? So.
Right. Yeah. So I know the New Frontier one, which is done with OEM modules, right? So
right.
I understand that one for sure. Okay.
I mean, yeah, right. The first 3 exascale supercomputers have the same racks and the same infrastructure from a fabric perspective, right? With Slingshot, the same kind of arrangement with 32 blades and 32 switches per rack. The blades are changing from the IP they have, obviously, one being Intel, the other 2 being AMD, but otherwise everything else is the same. They're 600 kilowatt racks.
Right. Okay. So I guess where I'm going really is I'm starting to think that the optical solutions are going to give us we're still challenged, right, with the cabling, especially with this wall approach. If you get too much cabling, then we have gone.
I was going to say, if for the default dimension of that wall, is there I would say a standard topology, connectivity topology that has been discussed in the past, or is it?
Yeah, we've done a number with Molex actually. We did an auto topology with sort of 8 modules showing standard 8 modules connected. I've shown various. So we've only done sort of like 8 of them in when we did have it back in a rack format. But obviously, I mean, it would be very easy for us to do a mesh topology, right, or a torus topology with this. But if you have, because these modules can be switches as well, right? So they don't. The idea is they can be CPUs, GPUs, switches, FPGAs, anything. And so obviously, if you have a switch, then everything's probably going to be I/O. Well, unless you have a CXL switch and you have CXL media on the switch itself. But so you can have a lot of I/O cabled into one of these modules, right? So that's cable density is going to be a potential challenge depending on the topology. But in theory, you can do any topology you want, and that's the beauty of this as well. Is everything is completely configurable with the wires. It really makes sense when you go, so like Avicenna's optical cables are like 1 millimeter compared to, a huge bundle of copper wires, and they're terabit per second in each direction. And so Avicenna, have a very interesting LED technology that can go up to 10 meters, but it can't go through an optical switch or anything. But you can see that if you had that built in, like the concepts we've shown with Avicenna on the module itself, then you could do any density of wiring in this topology without getting too congested. And so I guess where I'm sort of beginning now, we're 4.5 years into this, where it's looking like the optical approaches might become more viable. We're talking about glass substrates as well, which is interesting from an optical perspective. So actually, to your point, actually, Olivier, going back to this, if this is a package, is this ends up being one big glass substrate or something like that? I don't know. Or can this sit on one big glass substrate? or is it some mixture of that? And I've been saying, why not get rid of the package altogether and actually go to the module itself as the substrate and the power supply PCB, you know, get rid of these solder balls on these packages and go straight to high-speed connectors or optical connectors, high-speed electrical or optical. So yeah, I was thinking that maybe there's some sort of, and this is where I need to do more work on immersion, is if you had a liquid wall that these would be inserted into. Obviously, there's the serviceability of a liquid wall, wherever you could section the wall off so that you could drain certain pieces if you needed to service modules. But would sort of mini immersion, vertical immersion tanks, like very thin swimming pool tanks that these modules plug into for this liquid cooling, and much simpler, get rid of all the piping that you have on conductive cooling. That seems to be of interest and opportunity, whereas this side is very serviceable with pluggable media and all the interconnect between these modules. But if we design this module correctly, we not only cool, if this plugs into an immersion tank, you've got direct attach of the kilowatt dies, multi-kilowatt dies into the liquid, and you have conduction cooling of the rest of the stuff plugged in also into the liquid to keep these cool without any air cooling in the aisle, but they're still pluggable, and we wire between them with these passive optical cables. So that's really where my head's going. I think I'm still wedded to this, and I think that it provides a very competitive alternative to this blade approach. This just looks super damned expensive and super damned specific, you know, to exactly what you want to do here, you know, these different types of IOs, etc. Whereas we're trying to be as generic as possible in our design, that you can step and repeat it, and you can wire up whatever topology. You know, you've got one grace here to, if this is one Rubin, you've got one grace to 8 die and another grace to 8 die, and that is it. Whereas with our approach, you could decide that at system configuration. So you've got this domain specific configurability depending on your application need. So anyway, so I guess my where I've got back to is I'm still believing in this. I've got a little bit scared of these, managing these pressure drops, managing the flow of liquid, managing the variability of the load of each of these modules, because these modules, when they're running a job, burn several kilowatts, and when they're not, they burn nothing. So anyway, I've just realized I'm going over time, so apologies, everybody. But so you know, that's where I'm going. I'm going to revisit this, and as well as revisiting our bring up module idea as well, and whether we should converge the two rather than keep them separate. So that's my update for today. Thanks, everybody.
Thank you. Bye.
Thanks.
Thanks, Alan. Bye.
Thank you.
Thank you. Bye.